penultimate speaker today is Amanda Weinstein from Iowa State University.
Thank you. I'd like to say thank you to the organizers for a wonderful meeting. I have a lot of hard acts to follow. And I would also, and I'd like to thank them as well for the opportunity to talk to you today about some of the highlights from the VERITAS observation program that have to deal with science relating to supernova remnants and pulsar wind nebulae. I would also like to thank my collaborators and to thank the funding agencies, NSF, DOE, and the Smithsonian in the United States, but also agencies in the UK, Ireland, Canada, and Germany who made VERITAS possible in the beginning or contributed to the support of VERITAS science and operations over the past 10 years. So others have introduced the general concept of gamma ray observatories to you over the course of the meeting, so I don't have to do that. But I would like to remind you at least of the basics of what VERITAS is and how it works. So VERITAS is an imaging atmospheric Cherenkov telescope array. And the basics of how it works is that we do electromagnetic calorimetry with the atmosphere. A photon or a cosmic ray, proton or nucleus, come in, interact with the atmosphere, produce a shower, and the secondary particles in the shower produce Cherenkov light. By putting a set of four imaging telescopes on the ground in southern Arizona, we can take a look at the distribution of the intensity of that Cherenkov light and use that information both to pinpoint the direction and energy of the initial primary photon that initiates a gamma ray shower, and to beat down the majority of the background from cosmic rays. So what is this by us in terms of our baseball stats, if you will, for the instrument? We have a relatively modest duty cycle, about 800 hours of dark time per year, a few hundred more of gray time. And we also have a relatively modest field of view, narrow field of view, at 3.5 degrees diameter. However, we have an excellent energy range of about 85 GeV to 30 TeV, which sits smack in the middle of the energy ranges covered by the Fermi Lat satellite on the one hand and HAWK on the other, with good overlap with both instruments. We also bring to the table, along with the other atmospheric Cherenkov telescopes around the world, the best angular resolution of the gamma ray observatories currently in operation, and that's better than 1/10 of a degree above 1 TeV. We're highly sensitive, and we have great effective area. All right, let's see if this actually goes the right way. So others have made the case for me beautifully over the course of the meeting that supernova remnants, the expanding shock wave left behind when a star dies in a supernova explosion, are implicated in the production of cosmic rays up to roughly the knee, and that this is a source of continuing interest. What I want to do for you here is simply summarize how that connects to the VERITAS observation program. So from the point of view of the shock wave itself, and which is what I'm going to refer to as the supernova remnant, excuse me, we think that electrons, protons, and heavier nuclei are accelerated, while in the case of the other relics left behind, potentially if the supernova remnant is a quark-lax supernovae, i.e. pulsars and pulsar wind nebulae, these are interesting for a variety of reasons, but are also interesting because they potentially play a role not only in accelerating and injecting electrons, but also positrons into our local spectrum. So from the point of view of the shell-type remnant itself, the shock wave, we tend to divide our observations roughly into two categories: younger historical supernova remnants and more middle-aged or older supernova remnants. The younger remnants are of particular interest if you're on a hunt for pevitrons and want to constrain the maximal proton energy that can be achieved within supernova remnants. That's because we think that these remnants are able to get to those energies only for a brief period early in their lifetime. And I will talk about 2 of these at the end of the talk. We also have more middle-aged supernova remnants in play, and because these have had a little more time to expand and grow, we can resolve their morphology better. And so not only can we, as with the younger supernova remnants, get constraints on models of particle acceleration, but we also start to be able to get a look potentially at processes of particle diffusion within the remnant and escape from it. All right. So the first highlight I'm going to talk about is the Pulsar Wind Nebula, and it actually gives me a chance to highlight a very nice program of cooperation between VERITAS and HAWK, where we follow up on HAWK sources. And this was reported on in much more detail yesterday by my colleague Nahi Park. So the bottom line is that HAWK reported a set of 19 new sources with 500 days of exposure. And we were able to do high angular resolution follow-up both with the Fermi LAT data and with VERITAS. 12 of those sources were not detected by VERITAS, and in some cases those non-detections are in fact constraining in the sense that we can say something about the likely minimum extension of the sources that have been observed by HAWK. We also, as you can see with these 2 plots here, picked up on one known, that is, we already knew it was there, and one new likely TeV Pulsar Wind Nebula. So the one on the left here is the known one. You can see SNR G54.1 plus 0.3, and that has now also been detected by the Fermi LAT, so it now has a GeV counterpart. On the right is the new one, and this is a brand new plot that Nahi showed yesterday with the full 72 hours of observation that have been added to this field. And what you can see is that of the 2 sources in this HAWK field of view, we detect one of them, which has an X-ray Pulsar Wind Nebula counterpart known as DA495. So this is a likely Pulsar Wind Nebula. Now, if I can get this to behave. There is, however, something else that I want to point out about both the map and the associated spectrum. If you look here, I apologize for the pointer malfunction. You can see here in blue the HAWK spectrum for this source in this region, and you can see in red the measured VERITAS spectrum. As far as the spectral indices go, they're a reasonably good match. On the other hand, in terms of the flux, not so much. This is a significant, I think roughly, not quite an order of magnitude, but a factor of a few above the VERITAS flux. On the right, if you take a look at the map, you might have thought I was being a little bit disingenuous, because in addition to this very strong signal here, there seems to be a lot of glow throughout the map. I'm not really entirely being disingenuous, but what is the current status is that as far as the remaining glow through here, this excess is not statistically significant after we account for trials. However, if you put the 2 together, you might be forgiven for coming to the conclusion that this is just the tip of the iceberg. I should also make one more note here. The sources that were not included in this analysis, that were not included in this follow-up, this is not an oversight. These tended to be sources that were seen with very significant extension by HAWK, and these are sources that are difficult for atmospheric Cherenkov instruments because of the nature of the background subtraction and the fact that these forces saturate part or all of the field of view to a degree that makes them difficult to detect. Now, second Pulsar Wind Nebula highlight comes from from an update to the Cygnus region survey. So if I could draw your attention here, I will not be covering everything that has been updated in the region. This is basically a paper that's in preparation. It uses basically everything taken in this region through 2013, roughly, and it's about 300 hours of data. And you can see that the two sources in this region, one is considered a likely pulsar wind nebula. This is VERJ 2031 plus 415, also historically known as TeV 2032. And there's also a supernova remnant here up to the right, usually known as gamma Cygni, which I'll talk about briefly in the moment. And basically, there's two regions in this map, this one and this one, where pulsar wind nebula may form counterparts. So what about TeV 2032? I should actually say one more word about context before I do that. If you look at this map here, there is an invisible elephant in the room. Hawk sees emission in roughly these locations, not necessarily at exactly the same positions. The emission it sees surrounding 2032 is much more extended and very bright at multi-TeV energies. So it's not necessarily well matched in flux. And the other thing is that we know from Fermi-Lat that there is a region of emission quite large, about 2 degrees in extension, known as the Cygnus cocoon, in between these two. And the question of how that extends to high energies and relates to what we see both with VERITAS and Hawk is a very sticky one. So what do we know from the update? There's a few things that have changed since the last time I talked about this. One is that we now know from an independent lat analysis that the pulsar that TeV 2032 surrounds seems to be part of a long period binary. And the other is that we're dealing with, we now see not only an extended excess with VERITAS, but also with the Fermi-Lat. So that's terrific. We now have a Fermi-Lat counterpart to the VERITAS pulsar wind nebula. You might think we want to close the book and say this is all that we have to play with. We're just dealing with a pulsar wind nebula, end of story. But not so fast. It's not quite that simple. There are still some outstanding questions. And one of the things to point out with the VERITAS spectrum, so you can see here the Fermi-Lat excess that may be a counterpart, and here is the VERITAS spectrum in black. And there is no evidence for a break up to 30 TeV. And it has been previously argued, given what we know about the source and potential Klein-Ashina cutoffs, that we would have started to expect to see evidence for a break if this is really a pulsar wind nebula. So what's really going on, how it potentially relates to possibly contamination from another hard spectrum source in the field, we don't know. But that's something we clearly need to work on figuring out. All right, I'm getting very low on time to say much about middle-aged remnants. So I'll just remind you of a couple of recent updates here very, very briefly. One is that with the update in the Cygnus region survey, we're now, and with increased exposure with Fermi-Lat, we're now able to do what we weren't able to do before, which is to say that there's a statistically significant enhancement of the emission that the lat sees from the entire remnant that corresponds with the emission we see from VERITAS. And this is basically, that means that we're actually able to do something we weren't able to do before, which is produce a common broadband spectrum just for that enhanced region, which seems very consistent with evidence for a break. All right, I don't think I have time to say too much about the results on IC443, which have been shown previously. I will just point out that it's another case of us being able to do really nice work with resolving the morphology of the remnant, which is an extremely interesting remnant, and that we don't see any clear evidence, in some sense similar to what we see with gamma Cygni, but slightly different. We see intensity variation over the remnant, but the broadband spectrum between the lat and VERITAS seems to show a very consistent spectrum across the entire remnant. Another word about IC443 in context is that we now know that there's another supernova remnant. here, sorry, not another supernova remnant, but another source, about a degree in extension that has been seen in the lat. So this is now another invisible elephant in the room. It surrounds and envelops IC443 with sort of the brightest region being up here. Is it an escape signature related to the remnant or not? We don't know. But the other question is, what are we going to see with IICTs? This is a harder spectrum source than IC443 itself. It doesn't show the strong break that's seen between GeV and TeV energies for IC443. Does that hard spectrum continue up to higher energies, and how can we connect that with what might eventually be seen by Hawk? And this is something where IICTs could be very useful if we can come to grips with these larger extension sources. Finally, just a quick couple of snapshots on the young supernova remnants and that program. I don't have time to talk about it in detail, but I want to highlight a few results from the TeVPA paper that has been recently been published. The new softer spectrum that has been measured by VERITAS now suggests a lower maximum proton energy than the models previously developed to describe the GeV-TeV emission actually suggested. And we can also now say from morphology tests that were done, and this is tricky because TeVPA was essentially a point source fuss, but we were able to do some tests of morphology that actually let us rule out emission, more or less, that is coming from the molecular cloud near TeVPA or from the southwest quadrant that tends to be very bright and greater than 20 keV X-rays. So this is quite interesting, and I invite you, if you want more details about how this analysis was done or on the modeling, to go look at the paper. And finally, I just wanted to comment very briefly on the updated spectrum from CASE. We see preference for either broken power law or a power law with an exponential cutoff over a power law at about a few sigma. And the break energy is on the order of a few TeV and is fairly consistent with the similar result that was shown by MAGIC at this conference. So I am out of time, but let me quickly summarize where I think the outlook is for VERITAS going forward. I think the takeaway that you should take away from this is that we have achieved, with deep exposures, some really beautiful resolution of middle-aged remnants that's starting to give us an idea of what's going on with particle diffusion and morphology, that we have achieved spectra that are starting to test models to revision or destruction. And going forward, I think the story is really all about the 3 E's. Exposure, deep exposure to get those high statistics views. Energy range, that is leveraging the information that we have both from the lat and below us and from Hawk above us. We're seeing that as we look deeper and put the stories together, that the pictures are starting to come into greater concordance, but we have a long way to go. And finally, the 3rd E is extension. I think it's becoming more and more important that we come to grips with this issue of dealing with extended sources with IICTs. We bring to the table a much higher resolution view of what many of these objects look like. And I think if we're able to do this, we'll finally be in a position to tease out what's going on in some of these very complex regions, such as the Cygnus region, or to attack some of these very interesting sources, such as Dominga, where we're able to where we want to know what role that might play in the production of the positron exit. So I think this is the overall trend. I think we've come a long way, and over the next few years, if we leverage what we're, the cooperation between the 3 instruments correctly and make progress on these techniques that are in the pipeline to deal with extended sources, I think the future promises to be very bright, very fruitful, and a hell of a lot of fun. Thank you very much.
Okay, oh, sorry. We have time for one question.
Maybe one quick, is it on?
Question?
Okay. One quick comment on the fact that historical remnants, supernova remnants, do not seem to be pevatrons. So this is a very interesting result. And the energy you get is actually in line with recent theoretical predictions. So this corresponds approximately to the energy you would get from Bell's instability in these few hundred years old remnants. So one important implication is that the theory also predicts that higher energies, so basically energy of the knee, if not even beyond, would be reached in supernovae exploding in dense winds. So this is a pretty important point also for neutrino astronomy, because this justifies looking at correlations between, for example, ice cube neutrinos and supernovae.
Okay, thank you. I believe that was a comment more than a question. I'm not sure if there's anything you wanted me to add to that.
This was a comment, indeed.
Okay.
I agree. Thank you.
All right. Let's thank Amanda again.